Okay, we're moving on to a new topic now. It's called aromatic chemistry. And the word aromatic comes from aroma, which is Latin for fragrance. And that's because historically a lot of molecules that were discovered that were fragrant had benzene rings in them, what turned out to be benzene rings. But it's actually not the benzene ring that makes them fragrant. However, the name stuck, and the current definition of an aromatic molecule is one which contains a benzene ring, which is sort of like the molecule that's illustrated on the right hand side there, with 6 carbon atoms in a ring all joined together, and some hydrogen atoms around the outside of the ring, and in fact double bonds, 3 bonds per carbon plus a ring of double bonds. So that's what defines aromatic chemistry now. And the first thing we're going to have a look at is the structure of benzene. And we'll start with the bonding and structure of benzene. And in fact, we're going to do a history. I don't think you're going to get examined on the history of the structure of benzene, but if we study it, we learn a few things along the way. So in 1825, the famous Michael Faraday. So back in 1825, as was his wont, he did a few experiments, and he worked out the empirical formula of benzene, which he extracted from whale's oil, whale fat, if you like. And the empirical formula that he found out was CH. It was CH, and then with access to mass spectrometers, of course, early mass spectrometers, he also worked out the relative molecular mass was 78. So the MR was 78. And from that, he got a formula. So he turned the formula from CH into C6H6. The next job of which was to try and work out what the structure of benzene was. And he and other scientists couldn't figure out for a long time. Eventually sort of worked with a linear structure such as this one, with lots of double bonds in a row. So we had double bond, single bond, and then something like this. And it would have a kink in it around that single bond, but that I didn't draw. And so that was the structure that they worked with. And if you count that, you've got 6 hydrogens and 6 carbons. Lots of double bonds, as we mentioned, and that would make it very reactive. Double bonds are very reactive, and it would make it prone to addition reactions. But that's not what they found when they did experiments. It wasn't reactive, and it didn't do addition reactions. And it fell to a scientist called Kekule in 1865, and he benefited from a dream. Right, he dreamt of a snake eating its own tail, and from that dream he came back into his lab and proposed a cyclical structure for benzene. And that cyclical structure is drawn in the middle of that snake there, where you might be able to see. I'll just draw it out slightly larger so that we can see it. So we have double bonds on alternate carbons like this, and each vertex has 1 hydrogen on it, which I won't draw. So this is just a skeletal formula, and it still didn't react as you would expect it to react, given that it's got 3 double bonds there. And Kekule proposed that it existed in resonance structure. So a resonance structure was proposed that existed like this, so like so. So you can see the double bonds are on the other carbons, and it flipped from one structure to the other structure, such that any approaching electrophile couldn't react with the double bond because it was switching all the time. So this was a move forward, And in fact, it was the first time that scientists had conceived of cyclical molecules, and it was the first time that scientists had conceived of what became known as resonance structures, which is still a theory today. And yet it still didn't explain the lack of reactivity, so the high stability that benzene has. It still didn't explain that. So that was in 1865, and then in 1922, Kathleen Lonsdale got her X-ray diffraction machine out and put benzene through it, and got a diffraction pattern like this. And let me just draw on it, and you can see that these marks here are the carbon atoms. So I'm just going to circle where the carbon atoms are. These are the hydrogens. Let me circle the hydrogens. Hydrogens around here, and the white is the electron density. And what she noticed was that the bond lengths were all the same. Bond lengths were exactly identical. All right. All of these bond lengths were the same length, and so she was able to, with her diffraction pattern, measure those bond lengths, and they came out to be 0.14 nanometers long. So 0.140 nanometers long, which is not what you would expect if you had either of these resonance structures with the 3 double bonds and 3 single bonds. Because a single bond is about 0.153 nanometers, and a double bond, being slightly stronger, is a shorter bond, and that would be 0.134. So this is a double bond, that's the single bond, and the bond in benzene is 0.14 in between. All right, so it appears from bond length that the bonding that exists between carbon atoms in benzene is some sort of in-between bond between that of a single bond and a double bond. So that all happened in 1922. Let's just put the date up there, 1922. You don't have to remember these dates. But that was also aided when they were working out the structure of benzene by some thermochemical data. All right, so the thermochemical data. So they did some hydrogenation reactions. So let's take cyclohexane, which has a similar ring, right, and yet only has 1 double bond. All right, so let's, for the purposes of this thinking, draw in our hydrogens, or at least the bonds to the hydrogens. Let's just draw the bonds to the hydrogens. All right, so the carbons with the double bond just have the 1 hydrogen. So this is cyclohexene. We'll just label that. So this is cyclohexene, and when that was taken and hydrogenated, all right, so when hydrogen was added to this bond, and so you turn that into cyclohexane. So let's draw out cyclohexane, and so the double bond disappears and the 2 hydrogens make single bonds instead. So now you have 2 hydrogens on each of the carbons, like so. So you have cyclohexane now. Cyclohexane. So the enthalpy change when that happens, and it's called enthalpy change of hydrogenation, that is an exothermic reaction, as you would expect, of minus 120 kilojoules per mole. It's minus 120 kilojoules per mole. So then they got to thinking that, what about if we imagined this structure from 1865, the one with 3 double bonds? What if we imagined that structure, and we could call that 1,3,5 cyclohexene. So let's draw it out. So let's draw the 1,3,5 cyclohexene with 3 double bonds. Okay, so what you would expect if you hydrogenated that, so let's put 3 hydrogens onto this double bond, that double bond, this double bond. If you did that, wouldn't you expect 360, 3 times 120 to make cyclohexane? All right, so this was the expectation. So minus 360 kilojoules per mole. To make cyclohexane, let's quickly draw out cyclohexane just to complete, just to keep us all making sense. So cyclohexane like that, I'll leave it with the skeletal formula so I don't have to draw the hydrogens. So that's what they expected, but then when they actually put benzene through this hydrogenation, so they took benzene and they actually, so let's do it in green, what they actually got when they took the real benzene was a different number altogether. Experimentally, they found that hydrogenation of benzene with 3 hydrogen molecules was minus 208 kilojoules per mole, much less than they expected, which they concluded was because benzene must be much more stable than this theoretical 135 cyclohexatriene. Because the bonds formed is the same, so the bonds broken must take a lot more energy if the enthalpy of hydrogenation is less than you would expect. So so the bonds must take more energy to break because the benzene is more stable than you thought. So they had to try and explain this stability, and then what eventually was come up with was a cyclical delocalized model of benzene, and we draw it like this. So we draw so that that whole work was resulted in the fact that the 3 double bonds didn't actually exist as 3 double bonds, and they didn't resonate between one structure and another structure. What they did was they were shared amongst all 6 of the carbons, and they formed a sort of ring around the carbons, and that is the model that we use today, and it explains all its experimental results, and we're going to delve into that in a little bit more detail now. So this model becomes known as the delocalized model of benzene, and delocalized because the electrons involved in the double bonds are free to roam around all 6 of the carbon atoms in benzene. So let's just write that down. How can we summarize that? So electrons free to roam amongst all 6 carbon atoms. Okay, so that's the delocalized model. What I'm about to say on this slide is it's very much not A level. It's above A level. It's a subject of at least a couple of lectures at degree level. But you might be interested, and in any case, if you can understand it, it will help you understand this delocalized model of benzene. And I want to just understand the way that carbon bonds in a bit more detail. So if we have a look at the electronic structure of carbon, so you might think that carbon, okay, so it's got 6 electrons here, 4 outer electrons. So it's got electrons in a 1s shell, so let's call that 1s. And then it's got electrons in 2s, and at a slightly higher energy level it's got, let's draw out the orbitals, the 3 2p orbitals, like so, and we know it's got 6 electrons, so the first 2 are going to go in the 1s shell, And wouldn't you think that the second 2 would fill up the 2s orbital before we get London bus rule applying and your last 2 electrons going into 2px and 2py? That's what you would think, but that's not what actually happens, and it's not what we see from the experimental data either, because carbon makes 4 bonds, and this electronic structure that we've just drawn out would only be able to make 2 bonds, because a covalent bond is the bonding between unpaired electrons, and of course here we've only got 2 unpaired electrons. So what actually happens in molecules such as methane, so let's change colour. What actually happens is, of course, the 1s electrons are not affected. They're like that. But what happens is that one of those 2s electrons gets promoted up into that empty 2pz orbital, and at the same time they sort of hybridize and they become a hybrid between an s orbital and a p orbital. And so the way we might draw this is, and this energy level is supposed to be in between that of the 1s and the 2s rather, and the 2p. So let's write our 2p up on here on the left hand side there. That was the 2p, right? And we have 4 orbitals made. That are the hybrid orbitals, like so, and those 4 second energy level electrons go 1 each into those orbitals, and these are called sp3 hybridized orbitals, because there's one, they're the hybrid of 1 s orbital and 3 p orbitals, so you call them sp3 orbitals. And so this carbon, and didn't we say that it's the sort of structure that you get in a compound like methane, which has 4 covalent bonds around the carbon, and you can see we've got 4 unpaired electrons. But you might remember in benzene, each of the carbons only makes 3 bonds. So reflect back on that, and we'll see a picture of benzene in a minute anyway. So what happens in something like benzene is that the electronic structure becomes slightly different. Again, we'll draw out the 1s orbital, blissfully unaware of what's going on, and you get a slightly different hybridization. You get 3 orbitals that are a hybrid of the s orbital and 2 of the p orbitals. All right, so they've got and you've got another orbital which is a normal p orbital. So this is a 2p orbital there. These are 2 hybridized orbitals because they're the hybrid of 1 s orbital and 2 p orbitals. And so our electrons go in here, and in here, and in here, and in here. And our 3 bonds that are made that are between carbons and hydrogen, so I put them in a different colour because these electrons are coming from other atoms, are 3 bonds that, the carbons make in benzene go into those 3 orbitals, leaving a 2p electron spare, unbonded. Okay, so then that understood. Hopefully you've understood that, and it doesn't really matter if you don't understand it. You're not examined on it, but that sort of explains the structure of benzene, because you'll remember that a p orbital, well, you may remember that a p orbital is like a dumbbell shape. So let's draw a double bond. Okay, so let's say here we've got carbon nucleus. Here we've got another carbon nucleus. And let's draw a single bond between s. This is called a sigma bond. So a bond between 2 s electrons. All right, s orbitals are spherical, you remember. All right, so we draw 2 spheres here, and the electrons occupy more time in that overlap area than any other place. and so that is what ends up attracting the two nuclei. So you've got a positive force attracted to this negative overlap area, and you've got another force there, and that overcomes the repulsion between the two nuclei, and that is a single bond, and it's called a sigma bond. But a double bond is actually called a pi bond, and that's because you've got this different shaped orbital. A p orbital is sort of shaped like that, with two sort of lobes like that, and we'll draw another p orbital here. Like so, and so your overlap occurs above and below, and so our attraction in our double bond is between this green overlap area and the nucleus, and there, and also on the way down as well. That's the attraction in a double bond, and this is called a pi bond. So let's just label those. This green one, we'll call that a pi bond, P-I-E bond. I think it's from the Greek for P, which is from the p orbital, and this is the blue one is our sigma bond. So sigma bonds are single bonds, and the second bond that makes up a double bond is known as a pi bond because it comes from a p orbital. And so those electrons, let's look over to the right here. These electrons here that I've just circled in blue there, these electrons are in p orbitals. So now let's try and draw our benzene ring. Okay, so what I'm going to try and do is I'm going to try and do a 3D drawing. Right, so we've got a carbon atom here, and coming out of the page, let's draw a wedge shape because we're familiar with that being. Right, we've got another carbon atom, and another sort of wedge shape there. So another carbon atom, and then going into the page. Right, so we'll draw there. So that's supposed to be our hexagonal shape of our carbon ring, where the top carbons are actually going into the screen. And what I just want to do is I just want to try and draw these fourth electrons that are in the p orbitals. So what color should we do those in? Let's stick to green. Okay, so each of those have got one unbonded electron in their p orbitals, like so. Yeah, so the fourth electron, three of them are involved in bonding. Right, so let's just choose a different color and clarify where all our electrons are. Let's go purple. So if you take this carbon here that I've just run, right, it's one of its bonding electrons is in this bond that I've just to another carbon, and then one of its electrons are in this bond to the other adjacent carbon, and then of course don't forget that we've got a sigma bond to a hydrogen as well around that. So they are the three bonding electrons that are let me tick them, here, here and here, and our fourth outer electron is not bonded, and that's the one that I've drawn in green, which is in a 2p orbital. Up and below each of the carbons. Right, so now I've drawn that rather bad diagram. What we can do is have a look at a professional picture of what a benzene molecule looks like. Yeah, so staying with this delocalized model of benzene, let's clarify what you do actually need to know for A-level. And here we have a picture of the benzene molecule. And you can see the purplish spheres are the carbon atoms, and the hydrogen atoms, that's labelled here, the hydrogen atoms are the little grey ones. And why don't we label these black bonds? So all the black bonds are single bonds. Yeah, so they're single bonds, or you could call them sigma bonds. You don't need to know that they're in sp2 hybridized orbitals. That hybridization business is what you don't need to know. But what you do need to know is that, of course, you've only got 3 bonds. Look at this carbon here. Let's go a different colour. Look at this carbon here. It's got 1 bond that I've overwritten there, 2nd bond there, 3rd bond there. It's got 3 bonds, and you know that carbon has 4 outer electrons, and so the 4th one occupies a p orbital, which is drawn like so, up and below each of the carbon atoms. Okay, so that's what you need to know for A level, and those 4th unbonding, those non-bonding electrons exist in those p orbitals. Okay, and they don't just, the p orbitals don't stay there. What they do is they merge, and the merge looks like this here. You can see this sort of delocalized ring of electrons. So all those separate p orbitals sort of merge into one, let's call it a ring above the carbon atoms, and another ring below the carbon atoms, and those unbonding, non-bonding electrons occupy those 2 rings there. And those 2 rings make the benzene molecule very stable, because the charge, the negative charge, is shared across 6 electrons, and that sharing makes the stability. So that's what explains the bond lengths that are the same between each of the carbons, and it also explains the energy of hydrogenation that is much less than you would expect from three double bonds.